Hi, welcome back. Here we'll be discussing about thermodynamic cycles. On average, you can expect 7 marks question from this topic. First, we'll go through the syllabus. Here we have Carnot vapor cycle, ideal Rankine cycle, Rankine reheat cycle, air standard Otto cycle, air standard diesel cycle, air standard Brayton cycle, vapor compression refrigeration cycle. These are our syllabus. Now we will just expand and see what are things in each subtopic. First is Carnot vapor cycle. When we are studying second law of thermodynamics itself, you have seen Carnot cycle, but here it is Carnot vapor cycle. The only difference is that here we are using vapor as working substance. Earlier it was just air. Here, I hope you are remembering its shape in TS diagram. It was just a rectangular shape, right? Here also it is the same thing, but since we are using vapor, we'll be using saturation term of pure substance here. You know that there are four processes. Basically, for Carnot vapor cycle, we are having four devices: a boiler, turbine, condenser, pump, or compressor. In boiler, we'll be having water, and we'll be supplying heat to that. So heat transfer will be there. As a result, there will be phase change, and high temperature, high pressure vapor is formed that is fed to turbine. From turbine, the steam will expand. As a result, the turbine will be producing some useful work in the form of shaft work, and by the end of expansion, the steam temperature and pressure is reduced to an extent that cannot be reusable for any power production. Then it is fed to condenser. From there, the phase change happens. The steam changes to saturated liquid state. But and then pump is used. Using pump, it is fed to boiler condition. But for Carnot vapor cycle, we are not using a pump. Instead of pump, we will be having a compressor. The reason you will be seeing when you are learning that the problem with compressor is that it needs a lot of power, or a power requirement as comparable to the power produced by turbine. So as a result, the net power output will be, or net work output will be very less, as the compressor require a lot of work. So that is one of the disadvantages. There are other problems also practically using Carnot cycle as a practical cycle. Even though this is a maximum, the Carnot cycle is a maximum efficient cycle, we cannot use for this practically. So in order to make use of this practically, we have to make some modification. Thus the Rankine cycle is born. Rankine cycle is nothing but a modified Carnot cycle. Here also we will be having four basic devices which we explain for Carnot cycle, like boiler, turbine, condenser, and pump. Here, instead of a compressor, we are having a pump for Rankine cycle, and pump require very less power. So the net power output or net work output from the Rankine cycle is reasonably good for any practical power plant. So we can go for it. And in Rankine cycle, you will come to know about the term SSE, specific steam consumption, and that is one of the important term. But after having some modification also, we will be facing some problems. So again, we will have to modify. We will have to do some modification. There are some general modifications are there, like regeneration, reheating, and others. But in our syllabus, only reheating is there. We don't have to learn about regeneration. There comes the regenerated, not sorry, reheat Rankine cycle or Rankine reheat cycle. But before that, we have to see what is the efficiency of Rankine cycle. Efficiency is defined as net work divided by heat supply, right? For Rankine cycle, we are supplying heat when it is going through the boiler, and what transfer is happening when it is in turbine, as well as in pump also. So net work we have to take. So efficiency will be net work divided by heat supplied. Now coming to Rankine reheat cycle. The difference from Rankine cycle is that here we will be supplying heat twice. You know that in basic Rankine cycle, boiler is followed by turbine. Here also it is like that, but once the steam is expanded and it is about to send to condenser, it will be again sent to boiler where it is reheated and again it is sent to another turbine, and there also it will produce the power. So here in Rankine reheat cycle, heat is supplied twice, work is positive work is also getting twice. So accordingly there will be a difference for finding the efficiency also, because efficiency is net work divided by heat supply. So work is, we are getting net work from two turbines and heat supply is happening in two ways. So accordingly you can modify the equation for finding the efficiency. As I said, we don't have regeneration in our syllabus, so we don't have to learn it. Then we will go to air standard Otto cycle. Why it is called air standard? Because in this we are assuming that air is the working substance. That is why air standard Otto cycle has come. We assume that there is no chemical degeneration or chemical change is happening here. Only air is coming, just same air is going out. Anyway, some more assumptions are involved in this that I am not going to tell now. We'll learn when you go through it. Here also we are having four processes. The first one is reversible adiabatic compression. Second one is constant volume heat addition. Note that second process is constant volume heat addition. We are adding the heat at a constant volume process. Third one is reversible adiabatic expansion, and fourth one is constant volume heat rejection. Then we will be representing the same cycle in PV and TS diagram. Afterwards, we will find the equation for finding the efficiency of air standard Otto cycle. Then we will see a new term called compression ratio, how the compression ratio is related to efficiency. That means what will happen to efficiency if compression ratio is increased or decreased. Then we will see the terms like mean effective pressure and its significance or its effect on other parameters. That's all for air standard Otto cycle. It's pretty straightforward. You can learn very easily. Similarly for Rankine and Rankine reheat cycle also. So far it was very easy. Again, the next topic is also very easy topic, that is air standard diesel cycle. Only thing is that here the efficiency equation is slightly bigger, but after writing it for a couple of or 5 times, you will remember that I am pretty sure, because everybody does that. Here also we are having four process. Now we are talking about air standard diesel cycle. Here also we are having four processes. First one is adiabatic compression. Second one is constant pressure heat addition. Note that in earlier case that for Otto cycle the heat was added in constant volume process, but here it is heat is adding in constant pressure process. Third one is adiabatic expansion, and fourth one is constant volume heat rejection. Same way will be same as Otto cycle, will be representing this cycle in PV and TS diagram. Thereafter we will see the terms like compression ratio, cutoff ratio and expansion ratio, like R, RC, RE. They're all the short form for compression ratio, cutoff ratio and expansion ratio, and we will see how they are related to each other. There will be an equation that connects all the three. Then we will find the equation for finding the efficiency of air standard diesel cycle, and we will see the effect of RC and R on efficiency also. Later we will see the effect of cutoff ratio RC on other parameters like heat supplied, heat rejected, mean effective pressure, network also. That means how these things will be varied when RC is varied. It's very important. As far as gate is concerned, there were so many times the direct question came from this topic. So we have completed this, but still something are left. We will see what are they. Now we will compare Otto cycle and diesel cycle, but since both are different cycle, we cannot directly compare them. For comparison, what we will do is that we will fix two parameters similar for both the cycle. Then we will see how the efficiency is different, how the network is different and all. There are three ways we are usually compared. The first one is by fixing compression ratio and heat addition for same, that is seeing compression ratio and heat addition for both cycle, and we will see various parameters, especially efficiency, network and all. Next one is by saying compression ratio and heat rejection. In the first case it was saying compression ratio and heat addition. For the second case, saying compression ratio and heat rejection. These are all really beautiful things. I'm sure you'll enjoy these things. Third thing is same maximum temperature and heat rejection. Again, let me tell you one thing. Now you may be new to these things, so when you are hearing this, you may be having some alien feeling about these things. But I'm promising you that when you go through this, you'll really enjoy this. Yes. Thereafter, we'll be going to the engine parameters. There are so many parameters that we'll have to learn. There will be equation for that. There used to be a question from these terms also. First one is indicated power or IP. Second one is brake power. Third one is mechanical efficiency, indicated thermal efficiency, brake thermal efficiency, indicated specific fuel consumption, brake specific fuel consumption, volumetric efficiency, mean effective speed. These are all terms we have to learn and understand. We should be knowing the equation for finding these terms. Many times I have seen direct questions from this topic. Thereafter we have dual cycle. Yes, dual cycle. It's a combination of diesel cycle and Otto cycle. Here, heat addition is happening in two different ways. That is, both at constant volume process and constant pressure process. In Otto cycle, it was constant volume heat addition. In diesel cycle, it was constant pressure process. In dual cycle, heat addition is happening in both ways, except that everything is same as other cycles. And that's all about air standard diesel cycle and air standard Otto cycle. And as I told you, it's direct and it's easy. You can easily learn this, and only few equations are there, and things are all pretty directly connected to each other, so you can understand and learn easily. Next comes air standard Brayton cycle. Here again we will be using air as working substance. This is being used at the power plant for aircraft, especially for jet engine and all. We will be using this cycle. Here we will be having some basic terms like work ratio, back work ratio and all. We'll have to understand that. Now we will come to what are the processes in air standard Brayton cycle. Here also we are having four processes: reversible adiabatic compression, constant pressure heat addition, third one is reversible adiabatic expansion, and fourth one is constant pressure heat rejection. Now think about the fourth process, constant pressure heat rejection. For jet engine and all, what is happening is that they'll be taking the air from atmosphere. It is compressed by a reversible adiabatic process. Then heat is added at constant pressure. Then reversible adiabatic expansion, in which we will be getting the work, and work is taken. Thereafter, it is just fed to atmosphere itself. That means only three processes are there. The fourth process is missing. Again, for the next cycle, it will be taking air from atmosphere. This sort of cycle is called open cycle Brayton cycle. Open Brayton cycle. But generally, we will be referring to closed Brayton cycle. But you should be understanding, having an idea what is an open cycle here is. Okay. And thereafter, we will be analyzing this. Means energy wise, each process will be analyzed. But before that, we will be taking various assumptions. That's very important. Then only we can do the analysis easily. We'll be doing the energy analysis for all the four processes, and we'll be getting some equations or relations for finding things in each process. Thereafter, we'll find the efficiency of air standard Brayton cycle, and it's very important. And we will see the effect of pressure ratio and efficiency, how this is related. That means how the efficiency will be varying when pressure ratio is varied. Then we will find the optimum pressure ratio for maximum work. Maximum pressure ratio that is possible, that also we will find. Thereafter we will go to next topic, means same topic but next subtopic, that is isentropic efficiencies of turbine and compressor. We assume that reversible adiabatic compression and reversible adiabatic expansion is happening in compressor and turbine, but in reality that is not happening. So they are not isentropic process anymore, right? So in order to give that deviation, we use a term called isentropic efficiency. So if we know that, we can get the final points and all. You will understand that it's very quite easy thing, but you have to understand. Right, later we will see the various methods for improving Brayton cycle and their effects, how they will be affecting the performance. Generally, there are three ways, that is regeneration, reheating, and intercooling. That's all about air standard Brayton cycle. This thing is also pretty straightforward. Once you know the thing and we are having the equation with you and we are having good understanding about the cycle, we can score the complete mark from this section. That makes us to start our final subtopic of this thing, that is vapor compression refrigeration cycle. So far we were making power from using the application in thermodynamics. We were making the power from the cycles. Now here we will be giving the power or work to the cycle, and it will give some desired effect like producing refrigeration effect. So vapor compression refrigeration cycle. For simplicity, we will call this cycle as VC cycle. What it is? VC cycle. Here we are compressing the vapor to achieve desired effect. That's why the name vapor compression cycle. Here desired effect is refrigeration, right? Here the basic idea is we compress the vapor, then remove its thermal energy by heat transfer. What is happening is that we will compress the vapor using a compressor. When we are compressing it, its temperature will rise, right? When it is at high temperature, we'll stopping. After stopping of compressor, it will be at high temperature. Thereafter, its heat is removed. Thermal energy is removed by heat transfer. When thermal energy is removed, what is going to happen is that it will change its phase and it will go to saturated liquid level. You think about boiling water case. When we are supplying heat to water, it will boil and there will be a phase change and it will become vapor, right? And just think about the reverse of that. If we are transferring heat back to atmosphere from the vapor of the water, what will happen? There will be phase change and it will become water again, right? The same thing is happening here. When we are transferring heat from vapor, it will change the phase and become saturated liquid. That's we are talking about vapor compression refrigeration cycle. The first step was compressing the vapor, and during compression its temperature will shoot up, and at that time it will be in superheated vapor condition. Then we will transfer heat from this vapor, thus its phase change will be there and making it to come to saturated liquid state. From that we will be using a throttling valve, so there will be a temperature drop in this case and it will again come to wet region. You can easily see this in a TS diagram, so things will be much clear, but for now just hear this so that it will be a good starting for your studies. So now our fluid is in wet state, right? And this is fed to evaporator. Here is what our refrigeration effect is happening. This fluid will be at very low temperature, maybe probably sub-zero temperature. So this fluid will be passed through some coils. This you can find in your freezer compartment of refrigerator. Okay. Now we are keeping our food products and refrigerator, which will be at normally when we are keeping it, it will be at normal atmospheric temperature at 30 degrees Celsius, right? But the fluid which is passing through the coil is at sub-zero temperature. What will happen then? There will be heat transfer from the food products to the fluid, right? Just think that you are holding a piece of ice. What will happen in this case? There will be heat transfer from your hand to ice. As a result, the temperature will drop from your hand. At the same time, the ice will become warmer and warmer, and finally there will be a phase change, right? The same thing will happen here also. As heat is being transferred from food products to the fluid, the temperature of the food product will lower. At the same time, there will be a phase change for this fluid and it will become saturated vapor thing. And now again, our the first step repeats, that is compressor will come here now and it will take the vapor, it will compress and it will fed to for heat transfer. Thus the cycle is continuous. Since we wanted the lower temperature continuously, we have to operate this in a cycle. Otherwise, once we made a particular lower temperature, we are just switching off the fridge. What will happen? After an hour or so, it will again come back to normal temperature because there will be always heat leak from atmosphere to this fridge. So in order to get a continuous effect, we should operate this thing in a cycle. That's why we are going for a cycle, vapor compression cycle. There are four basic elements involved in vapor compression cycle or VC cycle, that is compressor that you already seen. Then next one is condenser, where the heat rejection is happening. That means our fluids heat will be rejected and it will come back to saturated liquid state, and then we will have a throttling valve, thereafter evaporator, through which our main refrigeration effect is happening. You all know this, right? And this we will represent in this is VC cycle, and we will represent this in TS, pH and HS diagrams. There will be various use for each diagram, but mainly we will be depending on TS diagram. After that, we will analyze all the four processes and we will find the required relations like work transfer involved in compressor and so. Here also we will be making some assumptions, and that's very much important. Then we will learn about volumetric efficiency and expressions to find the volumetric efficiency. So that's all about vapor compression cycle or VC cycle. The knowledge of the topics of entropy and properties of pure substance are very much required here. So before going through this, you should be having a sound knowledge of about topics. Problems from VC cycle is similar to problems from properties of pure substance. The first thing you have to do when you get a problem is draw the corresponding cycle according to the case. Every time the cycle need not be the same. There will be slight modifications, but according to question you can draw the cycle. Once you are having a cycle with you, you will be having sufficient confidence to solve the problem. There are some people they already know the thing and they already did a lot of problems, so out of overconfidence they just skip the cycle part and they do this problem on their own, but the probability of committing mistakes are more on this here. So how much stronger you are doesn't matter, you should draw the cycle while you are solving the problem. During practice session you may not make any problems, but when you are in exam situation you will be under pressure, so probability of making mistakes are more. So I am strongly advise you that you should draw the cycle when you are practicing, and you should be drawing it when you are doing in the examinations also. Now that's all about our application part of thermodynamics. The good thing about questions from thermodynamic cycle is that usually they are straightforward. That I already told you, right? That means if you know the concept and you made sufficient practice, you can get full marks without much difficulties and confusion. 7 to 9 hours of preparation is needed for this topic. Again, it depends on person to person. It's my own just assumption that you need this much time. I took this much time because there are a lot of topics involved. Even though they are simple, lot of the topics are involved here, right? That's why you need this much time, and some people will be required more than this. Again, it's okay, it depends on each person to person. I'm talking that after attending the class you need this much time, so don't consider your class hours as 7 to 9 hours for our preparation. Just don't say that I attended 7 hours of class, so my preparation is over. Don't do that like that. You should be spending individual time for practice of this. So all the best for your preparation.